All right, we're going to talk about properties of radicals. And just a quick heads up, this lesson usually takes three or 4 days in a classroom, just breaking it down. But I'm going to put it all under one, and then you can skip around and see what you need to use. So first, vocabulary: a radical expression is an expression that contains a radical. For those of you who don't know what a radical is, or you've forgotten, a radical is just this symbol right there. Many people call it the square root. However, that's just one piece of it. Could be a cubed root, fourth root, fifth root. Okay. A radicand is the expression under the radical. So whatever's inside here, we call the radicand. Okay. So if you see that term, that's what that means. Okay. Radical expression with index n is in simplest form when, and you're going to see this a lot, so I'm going to explain it as we kind of progress through the lesson. But just the rules: no radicands. So in other words, the thing inside cannot have a perfect nth root or nth power as a factor other than 1. I'll show you what that means here in a minute. It's a little less confusing than it sounds. The radicand can't have a fraction, so there can't be a fraction under that radical bar. And there can't be a radical in the denominator of a fraction. Okay? A square root is a radical with an index n of 2. Most people are used to that square root symbol. A cube root is a radical with an index of 3. So an index, for those of you, what is an index? That's the number that goes right here. If you don't see a number there, it's a 2. Okay, we don't show the 2, because that's the first root we're worried about, other than the actual first root, which is itself. So cubed root, if it was the fourth root, it would look like that, and so on. Okay? All right. So when we're simplifying, remember the rules for simplifying. A radical expression is in simplest form when no radicands have a perfect nth root or nth powers as factors other than 1. No radicals contain fractions. So I'm going to have you fill this in quite a bit just so you remember. And no radicals appear in the denominator. Okay, hopefully this will get boring and monotonous of the fraction there. So for simplifying, what this first rule means is if we look at the 125, the radicand, we want to think of our perfect squares. So if you think we have x, so when x is 1, 2, 3, 4, 5, 6, 7, 8, and let's go out to 10, 9, and 10. Okay, if we have those there. So when x is those numbers, or is any of those numbers, so then we'd have x squared. So 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5, 25, and so on. 36, 49, 64, 81, 100. Okay? When you have those there, it's important to be able to quickly take a glance and say, well, are there any of those perfect numbers that go into this other than 1? We ignore 1 because 1 goes into everything. So when I look at 125, does 4 go into it? Does 9, 16? Well, 25 definitely does, right? So what I could do is I can break up the square root of 125 into square root 25, and 25 times 5 is 125. So I break that 125 up into 25 times 5, which then I can break even further, give each of those numbers their own root, root 25 times root 5. And the reason we do that is because the perfect root 25, the square root of 25, the number times itself to make 25, which is what square root means. What times what makes 25? Well, that is 5, right? So this becomes 5 times square root 5. Now I should check the square root of 5. Is there a perfect square that goes into square root of 5? Well, 4 is the only one smaller than 5, and it doesn't go into it evenly. So no, it's not. So you are done. That is its simplified form, 5 times square root 5. Okay, so hopefully you try these on your own. Also pause it. But I look at 80. Well, what goes into it? Well, does 4? Yeah, it does. Quick shortcut, if 4 goes into it, always test multiples of 4. So the next perfect square that's a multiple of 4 is 16. Does 16 go into it? Yeah, it does. It goes in 5 times. And if you're not sure, get a calculator. Do 80 divided by 4, 80 divided by 9, 80 divided by 16. Okay? Another quick note, an odd number can go into both even and odds, but an even number only goes into even numbers. So like none of these evens could have went into 125. But I'm going to test 4. 4 goes into it. 4 goes into it 20 times. 16 goes into it. 16 goes into it 5 times. So 16 times 5. So I took the bigger of the perfect squares. Because when I break it apart, it just means I don't have to reduce as far. Right? So this gives me 4. Square root of 16 is 4. Root 5. That is my answer. And usually you don't show the multiplication. You just say 4 root 5. Same thing here. Now if you would have used, let's say we would have used, with root 80, let's say we would have used 4. That would have given me square root of 4 times 20, which would have broken up to root 4 times root 20, which is fine. That's 2 root 20. But when you're done here, you have to look at this root. Is there a perfect square that goes into 20? And you'd look and you go, yeah, 4 does. Okay, so we go 2 times root 4 and times 5. Right? This 2 drops down, and then that's 20 breaks into 4 times 5, which the 2 just follows down, but then we have root 4 and root 5. We give them their own roots. And this 2 drops down, and this 4 becomes 2. So now I have 2 times root 5, which is 2 times 2. Okay. Those two multiplied together end up making 4 times root 5. It's the same answer, just took much longer. Okay. Check the next one out. Well, we have root 100 and root x cubed. So what I'm going to do is I'm going to break it apart and give each of those their own roots, especially if you have variables. Break it apart right away. Okay. And now I kind of treat it like 2 different problems. I kind of ignore this side over here for a minute. I say the square root of 100. Well, that's perfect, right? That's 10. Well, I'm done with that side. So now I can give this side some attention and ignore this side. Don't cross it out like I did. The square root of, the square root of x cubed. Well, a perfect square when we're dealing with variables, think the square root of x cubed, well, you can't take the square root of x cubed. You could take the square root of x squared, right? That's x. In fact, x squared, what square root gives me x squared? Well, that would be x to the, well, x squared times x squared is x to the 4th. So root x to the 4th is x squared. What would give me x cubed? Well, x cubed times x cubed, that's, remember your rules for radicals, right? X cubed times x cubed, you add these up, you get x to the 6th. Okay, well, the square root of x to the what gives me x to the 4th? Yeah, that's x to the 8th. So an even root can be just cut in half. So really what you're trying to do is get an even root here. What root's close to 3 that's even? Well, you could break this up as x squared times x under there. X to the 1st, right? Because 2 plus 1 is 3. So root x squared times times x, we would write as root x squared, and root x squared, well, we just said that that's x. And that root x just drops down. You can't get another even number out of that. There's only one left. And so now we remember we have the 10 here. We drop it down. So we have 10 times x times root x, or 10x root x. Now, like I said, this takes multiple days, this lesson. Okay? All right, let's try another one here. Let's break it apart right away. So we're going to go root 45, root x to the 5th. I'm going to kind of ignore this side for a minute. Just look at the root 45. So that's going to be root, which perfect number goes into it? Well, 9 does. So let's use 9 times 5. So the root of 9 times the root of 5, it gives me root of 9 is 3. 3 root 5. And then we'll remember we have this side over here, right? And so let's kind of ignore u over here for a minute, and remember we want an even number. The even that comes before x to the 5th is x to the 4th times x. X to the 4th times root x. That gives me, well, the square root of x to the 4th is x squared and root x. Okay. And now we remember we have this and we have all these pieces. Well, we have things on the outside. 3x squared is on the outside. And on the inside, we put those things together. 5x. And you're now done. All right, and let's go ahead and take a look at this. Notice there's a negative sign out here. So we're going to think of that as like having a -1 hanging out there. What I want you to do is just kind of bring the -1 down. It just kind of drops down with it. Okay, it'll drop all the way down to the answer here at the end. So we'll just say, hey, we're going to bring this piece just down. And we're going to simplify the 48. Well, a perfect square that goes into 48, well, any even number will for sure go into it, and odds could as well, but 4 goes into 48. A rule for 4, if you can cut it in half twice, that's how many times it goes into it. So if I cut 48 in half once, that's 24, and cut it in half again, that's 12. So let's use 4, okay? Root 4 and root 12. Root 4 is 2. Root 12 is root 12. But root 12, 4 goes into that as well. So you got to keep breaking it apart, okay? So that becomes root 4 by root 3, right? Notice I stopped writing them under the same radical and just broke them apart. That's okay to do. The 2 drops down. So I have 2 times, well, root 4 is 2 as well. This 2 just comes from here, right? And this 4 becomes that 2 and root 3. So 2 times 2 is 4 and root 3. And the negative, don't forget about it. It's following along. -4 root 3. All right. Hopefully you're getting it there. We're going to move on to the second rule. Okay. No radicals, radicands have perfect nth powers as factors other than 1. Okay. No radicands contain fractions. All right. Well, we look at this radican here. The square root of 8/100. So we have a fraction in under our radical symbol. So what we do right away is we break that up. And we say that's the square root of 8 over the square root of 100. We break it into its individual parts. We give each of those numbers its own root. Okay? Well, that takes care of that rule, but now we have a radical in the denominator. Right? The bottom number of the fraction. 100. Well, the good news about that, the square root of 100 is 10. Okay? And root 8 on top. Well, now you have to go back and check all your radicals. Is there a perfect power that goes into root 8? And the answer is yes. Root 8, if you want to bring that over here and just treat it like its own problem, breaks into root 4 by root 2, right? So don't forget, we could write it like this to begin with, 4 by 2, that's 8, and we could break that apart to root 4 by root 2. Okay, square root of 4 is 2, so we get 2 root 2. So on top, rather than having root 8, we're now going to have, in our numerator, it's going to be 2 root 2 over 10. All right. So those of you kind of looking at that and going, huh? Well, notice there's something on the outside. You got that 2 root 2 and you have the 10. That's like having a 2 and a 10. And if both things are outside of a radical, think of it this way, like the radical is a house. The things outside of the radical can play. The thing inside can't associate with that because it's in the house. These two are both outside. We can simplify 2 tenths, right? 2 tenths reduces to, well, 1 goes into 2, or 2 goes into 2 once, and 2 goes into 10 5 times. So that whole thing actually breaks down just a little more It's root 2 over 5. All right. Stay with it. You'll get there. Okay. So let's go ahead and we've got a fraction in our radical, so we're going to break it apart. Root 49 over root x squared. Root 49 is perfect. That's 7. And root x squared is perfect. That's just x. So hey, we've checked all of our boxes here. No radicals left. So it's just 7 over x. That was a lot easier. Okay. Well, let's check out this next one. 9/25. Let's break it apart. Root 9 over root 25. And I'm going to break that apart on the bottom. I'm going to call that root x squared. Okay, on my numerator, root 9 becomes 3. Okay, so this part became a 3. Root 25 becomes a 5. And root x squared becomes a x. That's 3 over 5x. All right. Let's try another one here. Okay, let's break it apart. So hopefully you're pausing and trying these as well. Root 24 times root x to the 4th over root 81. Okay, well, I look at it and I recognize root 81 is 9. Root x to the 4th is x squared. And root 24, well, that one's a little tougher, right? It's not perfect, so let's see if we can break it apart. Root 24 could be root 4 by 6. 4 times 6 is 24, so that's square root of 4 by square root of 6. Square root of 4 is 2. Root 6. 2 root 6. X squared over 9. And the way we generally write that, and I'm going to draw a little line to separate that work, is 2. The other thing on the outside is the x squared, root 6, all over 9. That way when you write it, you don't accidentally extend this symbol just a little, and you're like, oh, is that x squared under it or not? And it's not, so we don't want to confuse that, so we put it out there next to the 2. Okay, let's go ahead and try one more up here. Notice there's a negative. That negative is just going to drop down to the end. So we have root 18, root x to the 6th, root 25, pieces that break apart, perfect, that's 5. So I like to write them as I'm doing them. That's x cubed. And that's root 18. Well, root 18, let's show some work for that one, okay? Root 18, let's simplify that. Root 18 can become root 9 times 2. Root 9 and root 2, which is 3 root 2. Okay? So all that equals 3 root 2 times x cubed on top over 5. And we want to put that x cubed next to 3, so we're going to go 3x cubed root 2 over 5. And the thing you never want to forget, always look back, you have that negative there. So that negative goes on the outside. Right? Don't forget about the negative. So we're going to bring that negative and put it on. All right. Well, hopefully you got it. We're going to move on to cubed roots. This would be day 2 of my lesson, by the way. All right, cubed roots. So no radicals have perfect nth powers as factors other than 1. No radicands contain fractions. And no radicals appear in the denominator. All right, so cubed root. This 3 means what number times itself 3 times makes 8. So remember the table we had up here where we had x and we had x squared. We're going to add to that. Okay, we're going to call it x cubed. And I'm not going to go quite as far. I think let's go to like 6 this time. So 1 1, 1 times 1 times 1 is 1. 2, 2 times 2 is 4, times another 2 is 8. 3, 3 times 3 is 9, 3 times 3 times 3 is 27. 4, 4 times 4 is 16. 4 times 4 times 4 is 64. 5, 5 times 5 is 25. 5 times 5 times 5 is 125. And 6, 6 times 6 is 36. 6 times 6 times 6 is 216. All right, let's actually end right there. Now you can keep going and go all the way up to 10, but I think that'll be good enough for what we need. So you just use your calculator. Keep going if you have to. So the cubed root of 8. So what number times itself 3 times makes 8? Well, notice my cubes. That is, well, 2. 2 times 2 times 2, right? Cubed root of 8 is 2. What's the cubed root of negative 8? Well, I'm going to stop or pause for a minute. If you look at, remember square roots? If I said, what's the square root of negative 4? And you say, well, negative 2? Well, that would mean negative 2 times negative 2 makes negative 4. And negative 2 times negative 2 is actually positive 4. Well, how about positive and negative 2? Well, those numbers aren't the same number. One's positive, one's negative. It has to be what number times itself. So the answer here, you can't do this. However, when you're doing a cubed root, a negative times a negative, well, that's a positive, but then you put a third negative in there, that equals a negative. So you're saying, what is the cubed root of 8? And then make a negative. Cubed root of 8 is 2. Well, you want negative 2. Negative 2 times negative 2 is 4, times negative 2 is negative 8. Notice as I've written these, I've just kind of added a piece. Well, the cubed root of 8x cubed. Well, we could break that apart. We could call that the cubed root of 8 and the cubed root of x cubed. Well, the cubed root of 8 is 2. We know that. The cubed root of x cubed. Well, the cubed root of x cubed. Let's think of our cubed roots. The cubed root of x cubed. Yes. Number time, or what variable times itself 3 times makes x cubed? Well, that would be x, yeah. X times x times x is x cubed. What if I wanted x squared? Well, you'd have to think x squared times x squared times x squared, right? You'd have x squared times x squared times x squared. Well, that's 2, 4, x to the 6. X to the 6, the cubed root of x to the 6 is x squared. Well, what gives me x cubed? Well, x to the third times x to the third times x to the third is x to the 9. Notice I'm counting by 3s. 3, 6, 9. So that power in there, if it's a perfect cube, has to be a multiple of 9. Just like when it was a square root or the second root, it had to be a multiple of 2. Okay? Well, cubed root of x cubed, these kind of just cancel, right? You end up with x. That's 2x. Let's check this one out. This one breaks into cubed root of 8 and the cubed root of x squared. Well, the cubed root of 8 is 2. The cubed root of x squared, well, notice you can't get a perfect cube out of that. You don't have enough. You need 3 at least. You only have 2, so you just leave it. You can't do anything with it. Your answer is 2 cubed root x squared. This one here, cubed root 8, cubed root x to the 6. Well, cubed root 8 is 2, and we've just talked about this, right? It's a power of 3, or it's a multiple of 3. How many 3's go into 6? Well, that's 2. So this is x to the second. Okay, 2x squared. All right, that's a quick lesson on cubed roots. Let's try a few more, and they're not going to be perfect this time, though, okay? So we're looking at simplify the expression. The cubed root, we'll break it apart. Cubed root of 8, cubed root of x to the 5th. The cubed root of 8 is 2. Cubed root of x to the 5th, well, we can break that up into a perfect cube. Okay, we can call it x to the 3rd and x to the 2nd. Why? Because 3 plus 2 is 5. That means I have the cubed root of x to the third and the cubed root of x squared. And the cubed root of x to the third is x. So I have 2 times x times cubed root x squared. I can't do anything with x squared. There's not enough of them. I need at least 3. Okay, there's that negative. Remember the negative, right? We'll bring that down. Okay, we're going to break it up as cubed root -8, cubed root x to the 7th. Cubed root -8 is -2. This breaks into, well, we can get at least, like 3 goes into 6, that's close to it, so we'll go x to the 6th and an x to the 1st. Right, that 6 and 1 is 7, so we still have our 7 under there. And then we could break that up into cubed root of x to the 6th and cubed root of x. And bring down that -2. The cubed root of x to the 6th, well, that's x squared. And cubed root. Make sure that doesn't look like an extension of the power, x. You don't want the 2 and the 3 to look like a 23rd power. Oh, you know what I forgot? See, I did it again almost. Forgot this negative. Got to bring that negative in there. So a negative and a negative end up making these 2 negatives become positive. So it's just 2x squared cubed root x. 2 negatives make a positive. Holy moly. Okay, let's try this one. I'm going to go ahead and break it up. Cubed root -16, cubed root x cubed, cubed root y to the 8th. Okay. Hey, I know this seems a little confusing. You do your best here. Cubed root of -16. Well, remember our perfect cubes, right? Well, 8 goes into 16. Okay, well, let's use that. We can break that up as to cubed root of -8 times 2. And notice I made it -8. If you have a negative, just put it with the perfect cube. Okay, so I'm going to ignore these. Remember, I'm going to pretend they don't exist for a minute and simplify this. This is going to be the cubed root of -8 times cubed root of 2. The cubed root of -8 is -2 times cubed root of 2. Okay, and now I'm going to kind of ignore this one, and I'm going to simplify this piece. Okay, so I think I'll bring it down here. Cubed root, well, actually I don't need to bring it down there because cubed root of x cubed is just x. So I'm done with that. I'm done with this. So I'm circling my ends here. Let's deal with this one now. Okay, if you want, you can pretend you're ignoring all those. Okay, and cubed root, well, to the 8th, well, let's use y to the 6th. That's the closest one to 8. That's perfect. And then y to the 2nd, right? That's still 8 of them, which is cubed root of, y to the 6th and cubed root of y squared. Cubed root of y to the 6th is y to the 2nd and cubed root y squared. That almost looks like a 23rd again. Okay, so this becomes that. And now I'm done with that. So the pieces I'm done with are all the circles. Those are my dead ends. So I have -2 on the outside. I have an x on the outside. I have a y squared on the outside. And in my cubed root symbol, I have a 2 and I have a y squared. Put them all together. All right. Well, let's try another one here. I'm going to break this apart. We're going to have cubed root of 27, cubed root of x on top, cubed root of 125 on bottom. Notice I've got this part, well, no radicals contain fractions, so we're taking care of that right now. right? And no radicals appear in the denominator. That's the next thing we have to take care of, because now we have a cubed root 125. But that root 125 actually becomes 5. Remember, that's a perfect cube, right? Cubed root of 125 is 5. Okay? And then cubed root of 27, well, that's also a perfect cube. 27 is 3. So duplicate that table there, 3. So this is 5. This is 3. And, well, I don't have enough here, so we just leave it. And that's all you can do. You can't reduce to 3/5, so you're done. All right. Cool. Okay. Let's go ahead and try the next one here. I'll break it apart. Cubed root, 56. Cubed root, x to the 5th. Cubed root, y. Over. Cubed root, 27. Cubed root, y to the 3rd. All right. Well, cubed root 56, I think I'm going to have to simplify. So is there a perfect cube, one of our perfect cubes that go into 56? Well, 8 does. And I think that's it, right? Well, we'll have to try 8 then. We will say, I'm going to go ahead and show my work for that piece right down here. Okay? So we're going to say cubed root 56. All right? And that's going to be cubed root 8 times cubed root, well, 8 times 7. Cubed root 8 is 2, so I get 2 cubed root 7. All right. So kind of our work area here. So we have on the numerator, we have 2 cubed root 7. That's our 56. And cubed root x to the 5th, well, that can be cubed root x to the 3rd times x squared. And cubed root y we can't break up. All over, hey, this is cubed root of 27 is perfect. That's 3. And cubed root y cubed is perfect. That's just y. We're getting closer. Okay, we have a 2. We have a cubed root 7. Well, we have a cubed root x cubed we can break apart, and x squared, so let's do that here. So we have cubed root of x cubed, that's just x, and cubed root of x squared, I can't do anything about. So we have x cubed root x squared. So, you know, let's rewrite this here. This is going to be 2, and then we have the x, and we have cubed root x squared and times y. Okay, so this part becomes just x. We have our x squared and y still inside. That x comes on the outside. And you know what I forgot in there was a 7. So let me rewrite that. We got the 7 also. 7x squared y. Okay, so an end, an end, an end, an end, and an end. Okay, the 2 and the x are on the outside. The cubed root 7, cubed root x squared, and cubed root y are on the inside. All over 3y. There we got it. Probably could have done with a little more work area on that one. Hopefully you have more work on your paper, more area to work. Okay, by the way, that would have been the end of day 2. All right. Day 3, rationalizing the denominator. Rationalizing the denominator just means you're getting the radical out of the denominator. So remember our rules. Okay, no radicans, perfect in powers, factors other than 1. No radicans in the or contain fractions. And then no radicals appear in the denominator. All right, of the fraction. So what we need to do, and I'm going to show you how to do this, and I'll fill these blanks in as we go. So we would break this apart, right? We would just call this root 17 over root 2. All the ones we've done in the past have had perfect roots in the bottom. This one does not. So we still need to get the radical out of the denominator. The way we're going to handle that, we're going to take the root 17 over root 2, and we're going to multiply it by a form of 1 to eliminate the radical from the denominator. Okay? By a form of 1 to eliminate the radical from the denominator. The form of 1 we're going to use is root 2 over root 2. Okay, notice root 2 divided by root 2. This thing right here is 1. Root 2 divided by root 2 is 1. So you're not changing the value. You're just multiplying by 1. Right? So you have the same value. But when you multiply across, root 2 times root 2 is root 4. And root 17 by root 2, well, you can multiply those. That's root. Sorry about that. Oh, my eraser isn't working there. 34. Okay? Well, you're saying, well, how does that help? Well, root 4 is just 2. Right? So root 2 times root 2 is root 4, but really, when you simplify it, you get the number inside. Anytime you multiply a root by itself, a square root by itself, you get the thing inside, which is 2. So the radical drops. You no longer have a radical in the denominator, and on the top, you have root 34. So root 34 over 2. Now you can't simplify that because 2 is on the outside, 34 is on the inside. If it's on the outside, it can't play with the stuff inside, right? They can't associate. Okay, that is rationalizing the denominator. So right there. So we tried it again here. Oops. Oh boy, I switched my page there. Here we go. So we got root 10 over root 3x. Root 3x is not perfect, so we're going to multiply it by that special 1. That's what I call it, the special number 1. Probably got that from Mr. Vogel. Okay, root 3x over root 3x is 1, right? So root 3x times root 3x. Remember, anytime you multiply a root by itself, you get what's in there. Now I'm going to show that it's 9x squared. Like 3 times 3 is 9, x times x is x squared. But 9x squared becomes, well, the square root of 9 is 3, and the square root of x squared is x. And then root 10 by root 3, well, that's root 30. And we still have that x. Remember, you can't reduce because this is inside or outside, this is inside. But your radical's out of the denominator, so you're done. Okay? Let's try another one. Deal with cubed roots now. Okay? And so when you're rationalizing a cubed root, you really are multiplying by, to get that radical out, you have to multiply by something that's going to give you a perfect cube. It was easy with perfect squares because if you multiply something by itself, that's always a perfect square. Perfect cube's a little different. 9 times 9 is 81, and 81 is not a perfect cube. However, 9 times something is a perfect cube, right? If we went back to our list of perfect cubes, 9 times, well, 3, right? 9 times 3 gives me 27. So I could call this cube root 3 over cube root 3. There's my number 1. That special 1. Cube root 3 over cube root 3 is 1. But cube root 9 times cube root 3 is cube root 27. 5 times cube root 3 is 5. Cube root 3. And the cube root of 27 is, well, that just reduces to 3. And on top we have 5 cube root 3. Okay, things on the outside don't reduce, and you can't reduce an outside with an inside, so you're done. All right, we'll try another one here. So hopefully you're pausing and trying them on your own. So we need to multiply by a cubed root, the same cubed root over itself, to get a perfect cube on the bottom that 4 goes into. So 4 times what gives me a perfect cube? Well, think of your perfect cubes again, right? Our perfect cubes. Well, 4 goes into 8. Okay, well, 4 goes into 8. So 4 times what is 8? Well, that's 2. So cube root 2 over cube root 2. There's our number 1. So cube root 4 times cube root 2 is cube root 8. 7 times cubed root 2 is just 7 times cubed root 2. You can't bring it in because this is outside, this is inside. So on the numerator, we're going to have 7 cubed root 2. And on the bottom, we're going to have, well, cubed root 8 is 2. Can't reduce 7 halves, and these can't work together because one's outside, one's inside. So you're done. All right, so one more here. We've got to multiply by a perfect cube, or by a cube to get a perfect cube. Now you're dealing with a variable. Now remember, in order for a variable to be a perfect cube, the power has to be a multiple of 2. So 7 is not a multiple of 2. So like 3, 6, 9, 12, and so on. So the number that we can make 7 become is the next multiple of, I think I said multiple of 2. It needs to be a multiple of 3. So 3, 6, 9, and so on. Okay, so 7 can become 9. So you can get b to the 9th here. Which means if I have 7 here and I need 9, I need 2 more. So I need a cubed root of b squared over cubed root of b squared. So that gives me cubed root of b to the 9th. And this gives me a squared cubed root b squared. Cubed root of b to the 9th, well, you can, how many groups of 3 can you make out of 9? Well, that's 3. That's b cubed and a squared cubed root b squared. All right. Or a squared cubed root b squared over b cubed. Okay, just so you know, we'd have one more piece on this day 3. Okay. The conjugate, when you change a sign between two terms in a binomial, it's called a conjugate. So the conjugate of a plus cd, well, here's your binomial, a plus cd, is a minus c root d. And the conjugate of a root b plus c root d is a root b minus c root d. Now you might ask why that is and why that's important. Well, I'm going to, I'll show you here in a minute. When simplifying expressions with a radical expression containing a sum or a difference of a square root in the denominator. So in other words, I don't just have a root, I have a whole piece here. I have a 6 plus root 3, and those things are together. So you can't break them apart. You need to multiply by the conjugate. And the whole premise behind this is using the difference of two squares. So if you remember earlier in the year, we did the pattern a plus b times a minus b. Like this, a minus b is the conjugate a plus b there. So if you were to multiply this, note you get a squared, and then you get negative ab, and then you get positive ab, and then you get minus b squared. Well, when you simplify, you get a squared, and this middle part, since you're negative ab and positive ab, they cancel. And then you have at the back minus b squared. So really your answer is a squared minus b squared, or that squared minus that squared. So if I multiply by the conjugate here, 6 minus root 3, really I'm doing that pattern. I'm doing the plus minus pattern. It's just, this would be like a, and this would be b. And this would be a, and this would be b. And so when I'm trying to use that to get rid of a radical in the denominator, I do that over itself because that's 1. But this times this, so it's a squared minus b squared. That's the pattern. So a is 6, so it's 36. B is root 3. Well, b squared then would be root 3 times root 3, or root 9. And on the top, you'd have 1 times 6 minus root 3. This times that. Now, that can be simplified quite a bit, right? 1 times 6 minus root 3 is just 6 minus root 3. Even if you distribute the 1, nothing happens. And you could do this, and they just stay the same. And 36 minus root 9, well, root 9 that's 3. So 36 minus 3 is 33. So my answer is 6 minus root 3 over 33. And now the radical's out of the denominator. I don't have a fraction inside my radicand, and you can't simplify root 3, so you're done. And by the way, you can't divide these two because it's not, the 33 would have to go into the 6 and the number right in front of the root because of that subtraction sign. You can't do it. Okay, so let's try another one here. Let's go ahead and multiply by 3 plus root 5 over 3 plus root 5, because that's the conjugate of 3 minus root 5. So I get 7 times 3, 21, 7 times root 5 plus 7 root 5, all over, well, remember this is like a and b, so a squared is 3 times 3 or 9. B squared is root 5 times root 5 is root 25, which we know as 5. So it becomes a squared minus b squared there. Okay, and that's 9 minus 5, or 4, and 21 plus 7 root 5. Now, some common mistakes. Some students try to add the 21 and 7, and you can't because 21 is counting, well, 21 is technically counting like root 1s, and 7 is counting root 5s. So you can't combine the two. So you're done. All right, let's try one more. And go ahead and multiply by the conjugate. Root 2 minus root 6 would become root 2 plus root 6 over root 2 plus root 6. Well, this would be my a and my b, a and my b. All right, there's the plus, there's the minus. Okay, so I would end up with a squared minus b squared is root 2, which is root 4. B squared is root 6 by root 6, which is root 36. And we distribute here root 22 and root 66. Yeah, man. Okay, which actually becomes root 22 plus root 66, and root 4 is 2, root 6 is, or root 36 is 6, so 2 minus 6 is negative 4. And there we've got it. Root 22 plus root 66 all over negative 4. All right. Okay, this would be day 4, and day 4, adding and subtracting radicals. In order to do that, you have to have the same radicand. So you have to be adding and subtracting the same thing. So I have 2 root 5s, and I have 4 root 5s for a grand total of 2 plus 4, or 6 root 5. So you're counting up how many root 5s you have. It's like saying, hey, I have 2 light bulbs and 4 light bulbs, so I have a total of 6 light bulbs, if root 5s were light bulbs. But there we got it. Can't simplify root 5, so you're done. Okay? You don't add the roots. You don't make it root 10 because you're counting up how many root 5s. You have 2 little root 5s and 4 little root 5s. If you don't have the same root, well, the next thing you try to do is simplify them. Well, I can't simplify root 6, but I can root 24. So that's like 2 root 6 minus 3 times, well, we can simplify root 24 to root 4 times 6. That's 24, so we get 2 root 6s minus 3 times root 4 times root 6, which is 2 root 6, minus 3 times 2 times root 6. Well, keep going. That's 2 root 6 minus, well, this is 6 root 6. Hey, isn't that convenient? We have the same root now. We have 2 root 6 minus 6 root 6, or how many root 6s? Well, you have 2 minus 6. 2 minus 6 is negative 4. Negative 4 root 6s. All right, let's try one more here. We've got root 27 and root 3. We can simplify root 27. So we get 3 root 3 plus 2 times root 9 by 3, which is 3 root 3 plus 2 times root 9 times root 3. 3 root 3 plus 2 times 3 times root 3, which is 3 root 3 plus That's 6 root 3. And that gives me 3 root 3s and 6 root 3s for a grand total of 9 root 3s. That's all there is to it in adding. Last piece is multiplying, and we've done a little of this. Really multiplying, just multiplying your radicals up. Root 3 times root 5, if they're both on the inside, you can multiply them. The insides would change. If they're on the outside, if one's on the outside like 5 is, and root 3, just call it 5 root 3. Root 3 times root 3, since they're both on the inside, we call that root 9. 5 root 3 plus root 9 gives me 5 root 3 plus, well, root 9 is 3. You cannot combine these because this is counting 5, this is counting root 3s. I have 5 little root 3s, and technically this is counting like root 1s, right? Root 1 is 1, so I have 3 root 1s, but we just call it 3. Okay? Here, root 14 minus root 40. Can't simplify root 14 because no perfect squares go into it, but root 40, root 4 goes into it. I could call that root 4 by root 10. Oops, root 4 times 10. All right, well, root 4 times root 10. All right, that's root 14 minus, this is 2, root 10. Can't put 14s and 10s together, nothing else I can do. Last piece, cubed root. Well, they're both cubed roots, so I have the cubed root of negative 4 times, or negative 2 times 4 is negative 8, minus the cubed root of negative 2 times negative 32 is positive 64. Cubed root of 8 is negative 2. And the cubed root of 64 is actually 4. So I have negative 2 minus 4, or negative 6. Hey, just one little thing. If I had like 2 root 2 times 4 root 3 minus 6 root, I don't know, 5. When you multiply this one, this is a separate problem. When you multiply this, this would be 2 times 4, which is 8. Root 2 times root 3, which is root 6. And this would be 2 times negative 6, which is negative 12. And root 2 times root 5, which is root 10. Can't put the roots together. You can't simplify them. You are now done. All right. Yep, that's all I got for you. Good lucky.